In this example, we are asked to show how the mixing of atomic orbitals around the central atom leads to the formation of hybridized orbitals. And the two examples we will look at are methanol and phosphorus pentafluoride. Now, the strategy for these types of questions is number one, to be able to draw the correct Lewis structure for the molecule. Number two, to be able to write the VSEPR class from the Lewis structure. And this will then help us to deduce the hybridization of the orbitals around the central atom. The question first asks us to look at methanol, which has the chemical formula CH₃OH. The Lewis structure for methanol is shown here, and as we can see, there are two central atoms, carbon and oxygen. So we'll look at the carbon atom first, and we can see that carbon has 4 atoms directly bound to it, 3 hydrogens and 1 oxygen, and no non-bonding electrons. And therefore, the VSEPR class for carbon will be AX4, and the hybridization is therefore sp3. Next, looking at oxygen, we see that oxygen has 2 atoms bound to it, carbon and hydrogen, and it has 2 pairs of non-bonding electrons. And so here the VSEPR class is AX2E2, and therefore the hybridization is sp3 hybridized. Looking at the carbon atom first, we can write the electron configuration for carbon, and since it is in group 14, and based on its position in the periodic table, the electron configuration can be written as He, 2s2, 2p2. So we can see that carbon has 4 valence electrons. So looking at those valence electrons in greater detail using the atomic orbital diagram, we see that we can fill those orbitals using the Aufbau principle, so from lowest energy to highest energy, along with Hund's rule and the Pauli exclusion principle. So the first electron will go in the 2s atomic orbital. The second electron will also go in the 2s atomic orbital, but it will be located spin down. Third electron will be placed in the 2p atomic orbital, and the fourth electron will be placed in a different 2p atomic orbital. So in order to create our sp3 hybridized orbitals, we need to use 4 atomic orbitals, and those orbitals are the 2s atomic orbital as well as all 3 of the 2p atomic orbitals. So mixing these 4 atomic orbitals together gives us our 4 sp3 hybridized orbitals. And of course, those 4 valence electrons would then be placed in our sp3 hybridized orbitals, as shown here, where we have 1 electron in each of the 4 sp3 hybridized orbitals. And so we can see that carbon has 4 half-filled sp3 hybridized orbitals. Next, looking at oxygen, we can see that the electron configuration, which being in group 16 and based on its position in the periodic table, can be written as helium, 2s2, 2p4. So in this case, we see that oxygen has 6 valence electrons. And again, looking at the atomic orbital diagram for oxygen, we will place those 6 valence electrons as shown here. The first electron goes in the 2s atomic orbital. Second electron also goes in the 2s orbital, but this will be placed spin down. Third electron goes in the 2p atomic orbital. Fourth electron goes in a different 2p orbital. Fifth electron again in a different 2p orbital, and the 6th electron gets placed in the first 2p atomic orbital, but it will be placed spin down. So now, in order to create our sp3 hybridized orbitals, we will mix the 4 atomic orbitals, the 2s atomic orbital and all 3 2p atomic orbitals, to create our 4 sp3 hybridized orbitals. And then the valence electrons will be placed in the hybridized orbitals as shown here, where the first electron goes in one sp3 hybridized orbital, second electron in a different sp3 hybridized orbital, third electron again different sp3, fourth electron goes in the fourth sp3 hybridized orbital, the fifth electron goes in the first sp3 hybridized orbital but is placed spin down, and the 6th electron is also placed spin down in the second sp3 hybridized orbital. So we can see that we have 2 pairs of non-bonding electrons, and this is where the non-bonding electrons occur, in 2 of the sp3 hybridized orbitals. Right? So those are the lone pairs. Okay? And we see that oxygen has 2 half-filled sp3 hybridized orbitals, so these are the half-filled orbitals, and 2 filled orbitals, that are the lone pairs on oxygen. In this question, we are asked to look at the bonding in phosphorus pentachloride, or PCl₅. The Lewis structure for PCl₅ is shown here, and as you can see, phosphorus has 5 chlorine atoms directly bound to it, and no non-bonding electrons around the central atom. So therefore, the Vesper class for phosphorus is AX5, and the hybridization is therefore sp3d. So the next step is to look at the electron configuration for phosphorus, which being in group 15 and based on its position in the periodic table, we can write as neon 3s2 3p3. And so we can see that phosphorus has 5 valence electrons that we should consider. Looking at those valence electrons in greater detail in the atomic orbital diagram for phosphorus, we see that those 5 valence electrons can be placed as shown here. The first valence electron goes in the 3s atomic orbital. Second valence electron also placed in the 3s orbital, but placed spin down. Third electron in a 3p atomic orbital. Fourth electron in a different 3p atomic orbital. And the fifth electron in the last remaining 3p atomic orbital. And those are the 5 valence electrons in phosphorus. So the next step is to form our hybridized orbitals, and in order to form the sp3d hybridized orbitals, we will have to use 5 atomic orbitals, which are the 3s atomic orbital, all 3 of the 3p atomic orbitals, and 1 of the empty 3d atomic orbitals. So mixing those 5 atomic orbitals together gives us 5 sp3d hybridized orbitals. And we also have the 4 unused 3d atomic orbitals shown here. So those 5 valent electrons will be placed as shown here in our molecule, where each one of the 5 valence electrons is placed in a different sp3d hybridized orbital. So we can see that the hybridized orbitals are half-filled.